Hello friends, in the previous video we have seen what are physical quantities and their units. In this video we are going to talk about scalars and vectors. So let us see what are scalars and vectors. Scalars are the physical quantities which have only magnitude, okay, and vectors are the physical quantities which have magnitude as well as direction. So that means for specifying a vector quantity you need to specify its magnitude as well as direction. Now what are examples of scalar quantities? Mass, length, time. Okay, these are scalar quantities. You really don't need any direction for stating length of an object, okay, or maybe distance between two cities, correct? Only magnitude is sufficient. Time, only magnitude is sufficient, maybe 5 minutes or 10 seconds or something like that. But then vector quantities, they have magnitude as well as direction. So now what are the examples? Examples of scalars can be mass, length, or you can say distance, or speed. So for speed I really need distance and time, correct? So distance covered in that much time, okay, so that will tell me the speed. But then what are vectors? Vectors would be displacement, or then velocity, acceleration, or momentum, and so on. Okay, now for vectors there are a few things that we need to remember. You know, I can add two displacements, I can add two velocities, I can add two accelerations, okay, I can add forces, okay, but I cannot add a force to velocity, or I cannot add a force to displacement, isn't it? I cannot add force to acceleration. So for addition the vectors have to be of the same type. But then, you know, we can also have product of vectors. In product of vectors, a vector can be multiplied by a scalar quantity, or it can be multiplied by another vector quantity. Okay, now when we multiply one vector quantity with another vector quantity, for example, maybe displacement vector and force vector, okay, that would give you something like torque, okay, or then distance vector or position vector and force vector, that would give you torque, okay, or then, you know, you can multiply acceleration vector by mass, okay, and that would give you force, isn't it? Force is equal to mass into acceleration, Newton's second law of motion, okay, or then you can multiply velocity by mass of body, that gives you momentum, okay. But when you multiply one vector by another vector, the resultant can be either a scalar or a vector. Okay, now example of two vectors, you know, multiplying and getting a scalar quantity would be work. So work done is equal to force multiplied by displacement. Okay, I would rather put one dot here. Okay, there is a reason why I am putting dot over there. Okay, or then torque or moment of force, I denote it by tau, Greek alphabet tau, that would be equal to the position vector multiplied by the force. This torque is also called turning effect of force. Okay, so how much turning a force can produce, that is given by torque. So these are two examples. You know, vectors, two vectors multiply and you get scalar, and here two vectors multiply each other and you get a vector quantity. Okay, so these things we will we will study in detail later, but for now let us see what is addition of vectors. As I already said, two vectors can be added if they are of the same type. I'll take a simple example. Okay, I am standing at point A, okay, I walk towards east, okay, and I walk through a distance of, let us say 50 meter. Now what I do? Now I walk towards south. Okay, again maybe this distance is 50 meter. this point was B and now this point is C. So distance between B and C is also 50 meter, and this BC is pointing towards south. Now again I travel towards west, let us say 50 meter again, and then finally I walk towards north and reach back to where I started from. So this point is D here. Now over here, if you could see, A to B towards east 50 meter, B to C towards south 50 meters, C to D towards west 50 meter, and then again 50 meter to the north, and I reach back to point A. Okay, now how much distance did I travel? I traveled 50 plus 50 plus 50 plus 50, that is total distance traveled is equal to 200 meter. But then if I think of the net displacement, I started from point A, I walked for 200 meters, but then the end result is I reached back at point A, isn't it? So what is the change in my position with respect to my initial position? My initial position is A, final position is A. Isn't the displacement 0? Yeah. So actually the distance traveled is 200 meters, but then displacement is 0. Okay. So displacement takes into account the change in position, or change in position with respect to the original position. So I'm not interested what is happening from A to B and B to C and C to D. Okay, what I am interested in is where am I, okay, after that much time. So I started from A, I'm back at A, so that means my displacement is 0. Okay, now there is one more thing. Imagine that I walk from A to B and then B to C and I stop at C. Now in that case, what would be my displacement? So wouldn't my displacement be from A to C? Isn't it? So I could say my vector AB plus vector BC is equal to vector AC. Correct. What if I put the magnitudes of AB and BC? Correct. So magnitude of AB and BC, that is 50 plus 50. Okay. And then that should be equal to, now 50 plus 50 gives me 100. But then if I measure AC, see this angle is 90 degree. Okay. Angle between east and south, it is 90 degree. So if I apply Pythagoras, I know that A to C is 50 root 2. So 50 plus 50 is not equal to 50 root 2, isn't it? So actually, so how could this equation be correct? This equation is correct because it is vector equation. So when I take into consideration the directions, then the vector equations will be true. Okay, so you just have to write the vector equation and take into consideration the directions and angles, and then you can get the final vector there. Okay, now we can have one law here, that is triangle law of vector addition. So what I did, I started from A to I walked to B, so this is one displacement. From B to C there is another displacement. So what I did, I connected my tail of my first vector with head of my second vector, and I got the resultant, isn't it? And that is what triangle law says. So if I have one vector starting from here, let us say PQ, and another vector, next vector is here QR. Okay, then my resultant vector, for getting the resultant, what I need to do is I just have to connect the tail of my first vector with head of the last vector. So here I can write the vector equation as PQ bar plus QR bar is equal to PR bar. You should remember that PQ bar, it is not magnitude. Okay, QR bar, it is not magnitude, it's a vector. Okay, when you say vector, it has got a particular magnitude and direction. Okay, so when you put a bar on top of this PQ, then that becomes a vector. Okay, now what if I start from point P here, then I go to Q here, then I go to R here, and then I go to S. So my P, Q, R, S, and finally T. So my vectors are like this: PQ bar, QR bar, RS bar, and ST bar. What is my resultant? My resultant would be PT bar. So I connect the tail of PQ bar with head of ST bar. Okay, now basically, this law would be called triangle law of vector addition, and this law would be called polygon law of vector addition. Now polygon law of vector addition is a special case of triangle law. I'll tell you how. My initial two vectors are PQ bar and QR bar, right? So what I'll do is I'll find the resultant of PQ bar and QR bar. Okay, that would be here. Okay, next vector is RS bar. So now what I'll do, I'll take PR bar and RS bar. I'll take resultant of them. Right, so my second resultant, if I call this R1, this is R2, R2 is PS bar. Now what I do, I take PS bar and ST bar, that gives me my final resultant R3 bar here. Right, so polygon law is nothing but special case of triangle law. Okay, now here my first vector was something, and then my second vector started from where the first vector ended, correct? So it was quite alright. Okay, what if both the vectors start from the same point? Let us see what happens in that case. Now my first vector is here. Okay, I call this vector OP. Okay, OP. So it would be OP bar. I'm going to call it P bar. Okay, my second vector also starts from point O. Okay, and then this is the second vector. This point is Q. I call it Q bar. Now what about the resultant of these two vectors? Okay, now for this you just have to imagine, okay, there is a ring over here at point O, and there is a string tied to it. Okay, two strings are there, and one person is pulling that string in this direction, other person is pulling this string OQ in this direction. Okay, so you have two force vectors. Okay, now you have to find the resultant. Now a little consideration or little visualization or imagination will tell you that this ring is going to go somewhere. It won't go in this direction, it won't go in this direction, but then it will be somewhere in between. But where exactly? Can we find out? What is the resultant of these two vectors? We need to find out. Okay, and since it is a resultant vector, okay, we have to be able to find out the direction also. Okay, now what I know here is this angle. Okay, this angle, I am going to call this angle theta. Okay, I want to figure out what is the value of the resultant. Okay, so now I am going to do a little bit of construction here. So what I am going to do is I'll draw a line parallel to OP here, maybe something like this here, and another line starting from point P, and it will be parallel to OQ. Okay, so second line would be like this here. Okay, and let us imagine that they meet at point R. Okay, my resultant is given by OR, so I will have to connect this and this is my resultant R bar. Okay, now you would say, how did you get this? Okay, so whatever I say here, I must be able to prove, isn't it? You shouldn't take it just because I am telling you. Okay, let us prove that. Now this line PR, okay, this line PR, actually my vector OQ, okay, vector OQ and PR, they are parallel. We know that OQ length OQ is equal to length PR, correct, and length OP is equal to length QR. So what I did, I basically completed a parallelogram. Okay, now one thing is there, you know, it is a property of vectors. You can shift a vector parallel to itself keeping its magnitude same. Okay, if you keep the magnitude same and move that vector, you know, parallel to itself, then the vector remains same. So can I say that PR bar is equal to OQ bar and that is equal to Q bar? Yes, I can say that. I would say PR bar is equal to OQ bar and that is nothing but Q bar. Okay, now if I have this PR bar as my Q bar, okay, I simply apply triangle law of vector addition. So by triangle law, I can say OP bar plus PR bar is equal to OR bar, and then that makes it P bar plus Q bar is equal to R bar. Okay, that is the simple proof of parallelogram law of vector addition. Okay, yes, I got the vector, but I need to know the magnitude, I need to know the direction, isn't it? So how do you do that? Again, little bit of construction. It is very easy and you will understand within no time. So I extend this here and I draw a perpendicular here. Okay, now what should be this point called? We call this point let us say point D. Here this is perpendicular, correct. Now one thing you would notice here is my OD, line OD is OP extended, correct, and OQ bar and PR bar are parallel, correct. So certainly this angle is also theta, right. If that angle is theta, then you know, let us do little trigonometry here. In triangle I would say PDR, triangle PDR. Okay, I am going to write some trigonometric ratios. I would say my cos theta is equal to cos theta, adjacent upon hypotenuse. Adjacent is PD and hypotenuse is PR. So PD upon PR, correct. Now what is my PD? I don't know. That is something that I constructed. But then PR, yes, I know PR. So I can say therefore PD is equal to PR cos theta, and PR is nothing but Q, correct. Q is the magnitude of vector Q bar. So Q cos theta. Okay, all right. Just like I put cos theta over there, let me put sin theta also. So sin theta is opposite upon hypotenuse. So that is RD upon PR, RD upon PR. So my RD is equal to PR and PR is Q sin theta. Okay, this is something that I have written for my future convenience, immediate future, right. Now since we have two right angle triangles here, okay, can we apply Pythagoras theorem to this? Yes, we can. Let me consider triangle ODR. So triangle ODR, which is a right angle triangle. So square of hypotenuse is equal to sum of squares of other two sides. So I would say OR square is equal to OD square plus RD square. Okay, all right, OD square plus RD square. But then what is my OD? My OD, is it not OP plus PD, correct? So OP plus PD square plus RD square. Okay, so now what is OP plus PD whole square? So it is OP square plus 2 OP PD plus PD square plus RD square. Okay, so now I have to do something more. I'll consider this triangle, this small triangle PDR. Okay, in triangle, right angle triangle PDR, PD square plus RD square plus RD square, is it not the hypotenuse which is PR square? Isn't it? PD square plus RD square is PR square. PD square plus RD square, I have that over there. Okay, so why not put it over there? So OP square plus 2OP PD plus PD square plus RD square is PR square. Do we know OP? Yes, that is P. Do we know PR? Yes, that is Q. So I'll just put it over there. So it is P square plus, I'll write Q square plus 2OP is P, 2P and PD. Okay, what is PD? Is it not Q cos theta? So 2PQ cos theta. Alright, and what is my OR? Isn't it R square? So then my R is equal to root over P square plus Q square plus 2PQ cos theta. I know the magnitude of P, I know the magnitude of Q, I know the angle between them, so I know the cosine of that angle, isn't it? So I can get the resultant of these two vectors P bar and Q bar, which start from the same point O and make an angle theta with each other. Okay, so I have been able to find, first of all, what I established that the magnitude of resultant, it would be given by the diagonal of this parallelogram constructed with the help of these two vectors. Okay, I got the magnitude of resultant, but what about the direction? Okay, I need to have direction, so for that I'll call this angle theta alpha. So this angle alpha. Okay, what do we do now? I have written the angle alpha there, but then I must find out the value of angle alpha. Am I going to be able to do that? Yes, we can, because we always know the trigonometric ratios, right? So what I'll do is I'll take tan alpha, and alright, so it is tan alpha, my bad. Tan alpha is equal to, tan alpha is opposite upon adjacent, so opposite is RD upon my, what is my adjacent? It is OD. So RD upon OP plus PD, correct? So my RD is equal to, RD is Q sin theta. Okay, Q sin theta divided by, now OP is P plus PD, PD is Q cos theta. So this is my tan alpha. So I know everything on the right hand side, Q sin theta upon P plus Q cos theta, right? I know angle theta, I know P, I know Q, so I know tan alpha. Is it not simple? Yes, it is. So this whole thing, it is called parallelogram law of vector addition. The proof of this may not be asked, okay? It won't be asked, but then you should know how this law is proved. Okay, so that is about it. In the next video we are going to talk about resolving vectors, which is going to be quite useful in solving the problems that you are going to come across in your AS level and A level physics exam. Thank you so much.